Hi, in this video I'm going to be talking about partial pivoting and how we use it along with LU decomposition. So partial pivoting is a way of sort of dealing with ill-conditioned systems. So what I mean by an ill-conditioned system is I'm just going to write down a 3x3 matrix. Let's say this is a coefficient matrix of some linear system, and if I was trying to calculate the LU factorization of this matrix, we have a problem because our pivot element in the first pivot is 0. So we'd have a divide by 0 error when calculating the lower triangular values of L in column 1. So partial pivoting, okay, essentially it means we perform a row swap operation and we swap the row such that the pivot element is the largest, or the value of the pivot element has the largest absolute value of all the numbers below it. So here you can see that 3 is the largest value in the column beneath our pivot element. So we're going to do a row swap, swapping rows 1 and row 3. Okay, so if we swap row 1 and row 3, row 1 becomes 3 minus 2 in 2, row 2 is left the same, and row 3 becomes 1, 0, minus 2. Okay, so that's the first pivot element done. The second pivot element, this one here, is 0. So again we're going to get a problem. So what we do is we can swap rows 2 and 3 around so that the pivot element has a larger value than the element beneath it. Okay, so if we do that, row 1 is unchanged. Row 2 becomes 0, 1, minus 2, and row 3 is 1, 0, 2. Okay, so what we have now is, if this is our coefficient matrix, and we'd also perform the same row operations to the constant vector b, okay, we'd now have we would no longer have an ill-conditioned system. Okay, what I'm going to do now is I'm going to do exactly the same row operations, but this time I'm going to apply them to the identity matrix. So the exact same operations as before. So this time row 1 becomes 0, 0, 1, row 2 is unchanged, and row 3 is 1, 0, 0, and our second row swap was row swap 3 and 2 around. Okay, so 1 is the same, and we have 0, 1, 0. Okay, what I've done here is I've actually calculated what we call a P, which is our permutation matrix. Now permutation matrices are useful because if I multiply P by A, I should get, or I will get, the matrix up here, which was our effect of applying those two row swaps. Okay, so let's just check that. So let's say that that's our original matrix. 1, 0, 2, 3, minus 2, 2. Okay, so if I perform this matrix multiplication, it's quite easy, because all you do is you look at which column, for each row you look at which column the 1 is in, and that's equivalent to the row. So if I multiply these two together, my first row will be row 3, my second row will be row 1, and my third row will be row 2. And you can see that's the same as what we had over there. Okay, so the first thing to note is that when we perform the row swaps, we get a permutation matrix, and that the effect of the permutation matrix multiplied by our original matrix gives you the effect of the row swap. Okay, so how does this relate to, or how does this change LUP work? Well, when we solved, if we solved a linear system of the form AX equals B with LU factorization, we replace A with LU, and then we let y, or the vector y, equals ux. So that therefore we have we can solve y equals ux, and then we simply have ly equals b, and that gives us our solution. Okay, so if we have a permutation matrix, so if we've applied partial pivoting, so if we had the same linear system as before, okay, what we've done is we calculate LU is equal to PA. Okay, so we perform the row swaps. Okay, so we perform the row swaps and A, and that gives us LU equals PA. Okay, so what we then have is we have a system. We'll be solving a system PAX equals B. Okay, well, another property of P is that P is equal to its inverse. Okay, that's a property of P. So if I pre-multiply both sides by P inverse, I get P inverse PAX equals P inverse B. Well, any matrix multiplied by its inverse is the identity matrix. That's just AX, and as I said before, P is equal to its own inverse. That's PB. Right. So now, instead of this, what I'm solving this. Okay. So if I calculate LU factorization for A, I'll get LUX equals PB. So we let our vector Y equals UX, and vector Y equals UX. So we let our vector Y equals UX. So therefore, we're solving LY equals PB, and then we're solving the Y equals UX equals Y. Okay, so that's how we, if we need to perform partial pivoting to solve a system with LU factorization, we first perform the row swaps to give us our matrix P. Then we calculate LU factorization on the resulted matrix PA, and then once we've got that, we solve Y. LY equals PB, and once we've got Y, we then solve for X with UX equals Y. Okay, let's have a look at an example of doing that. Alright. Okay, so this is example 6.7 in the notes. Okay, so we have a system, and I'm just going to write it down here. It's actually got the same matrix as we looked at before. So minus 2, 2, and 2. Okay, we have an unknown vector x1, x2, x3, and that equals our constant vector, which in this case is 10 minus 4 minus 8. Okay, so before we saw that P was equal to this. Oh, that's a 1. Okay, this was the example we looked at before, and so therefore PA was equal to 3, 1, writing down, minus 2, 1, 0, 2, minus 2, 2. Okay, so this was the this is our coefficient matrix with those two row swaps applied, and this is the corresponding permutation matrix. Okay, so now what we're going to do is we're going to calculate the LU factorization of this. Okay, so using, as we did before, or as we've done on a previous video. Okay, going down the first column, U11 is equal to A11, and in this case A11 is 3, and then L21 is 1 over U11 times A21, so that's 1/3 times 0, which is 0, and L31 is 1 over U11 times A31. Okay. If you're wondering where these come from, I suggest you, this is just look at the value, look at the equations for L and U in the notes, and it's also covered on a previous video. Okay, so that's 1/3, 1 equals 1/3. Okay, onto the second column. So when J is equal to 2, right? So we have U11 again. Oh, U12, sorry, is equal to A12 is equal to minus 2. U22 is equal to A22 minus L21 times, that's meant to be a U, U12. So A22 is 1 minus L21, which is 0, so it doesn't really matter what U12 is. So that's equal to 1. And L32 is equal to 1 over U22, A32 minus L31 U12. Okay, so that's 1 over 1. So that's U22 is just 1. A32 is 0 minus L31, which is 1/3, times U12, which is minus 2. Okay, so that's going to be 2/3. Okay, and finally, when j is equal to 3, we have U13 is equal to A13, which is equal to 2. We have U23 is equal to A23 minus L21 U13. Okay, so 23 is minus 2 minus L21. What was L21? That was 0, and U13 was 2, so that equals minus 2. And finally, at U33 is A33 minus L31 U13 minus L32 U23. Right, so A33 is 2, A33 is 2, yeah, minus L31, which is a third, U13, which is 2, and minus L32, which is 2/3, and that's multiplied by U23, which is minus 2. I'm running out of space here a little bit. And that is equal to 8/3. Okay, so after all that, we have our L matrix. So we'll have 1s on the main diagonal, 0s in the upper triangular elements, and L21 is 0, L31 is a third, and L32 was 2/3. And our U, so it's going to have zeros on the lower triangular elements. We have the same first row. Okay. Second row, so U22 was 1, U23 was minus 2, and U33 was 8/3. Okay, so what we need to solve this is we need a permutation matrix P. Sorry, what we need to solve this with partial pivoting is a permutation matrix P, and then we apply LU factorization to P times A to give us L and U. Right, so now we got those, what we're going to do is solve. Pick another colour, something I haven't used yet. So just to remind ourselves what P was. So P was 0, 0, 1, 1, 0, 0, 0, 1, 0. So that's meant to, let's tidy that up a bit, that's not good. Okay, we had P, we had L, which is 1, 0, 0, 0, 1, 0, and 1/3, 2/3. And U, which was 3 minus 2, 2, that's meant to be a 3, and 0, 0, 8/3, and the last thing we need is our constant vector B, which is 10 minus 4 minus 8. Okay, so the first thing we do is we solve for Ly equals PB. Oops, don't know what the bracket's doing there. Okay, so we solve that using forward substitution. So that's going to be our y's are our unknowns, and PB, so 0, 0, 1, 1, 0, 0, 0, 1, 0, and our B vector, sorry, -4, -1, -8. It's quite easy to actually calculate this, so this is -8, 10, -4. Okay, so this clearly shows that y1 is equal to -8. Okay, so 1y1 is equal to -8. And the second one's easy as well, so we got 1y2 equals 10. And the third one, y3, so we'll have y3 is equal to -4 minus 1/3 times y1 minus 2/3 times y2, and that equals -8. Okay, so we now have our y vector, so that's the first step, step 1. Step 2 is we solve, as usual, ux equals y. So once you've got y, you simply solve for ux equals y, so our u matrix x is what we're trying to solve for, and we just calculated y, which is -8, 10, -8. So this one was done by forward substitution, this one will be done by back substitution. So if we divide, so we've got 8/3 times x equals -8, so x3 would be -3/8 times 8 times, that's it, yeah, so x equals -3, so x3 equals -3, x2, so we'll have 10 plus 2 lots of whatever x3 was, which is -3, so that becomes 4, and finally x1 is, well, the coefficient of x1 is 3, so we're going to have to multiply by 1/3, we have -8 plus 2x2, minus 2x3, but so that's going to be plus 2/3, so that's going to be 1/3 of 6, so that's going to be 2. So that's our solution. So LU factorisation with partial pivoting is also known as LUP decomposition. So you perform the row operations on A, you calculate LU based on the PA. Okay, so once you've got P, L and U, you solve for Ly equals PB using forward substitution, then that gives you Y, and then once you've got Y, you solve Ux equals Y using back substitution.